Hey, what's up everyone? Welcome back to System Design Visualized. Today we're tackling something that comes up in almost every backend interview, the job scheduler. And more specifically, what happens when millions of jobs all fire at the exact same time. Let's break it down. So first, what even is a job scheduler? It's basically a system that runs tasks at a specific time or when something triggers them, and you use them everywhere. Sending daily reports at 9 a.m. Triggering a welcome email 30 minutes after someone signs up. Processing payments at the end of every month. Retrying that failed API call with a Backoff. Running analytics pipelines every hour. Simple concept, but incredibly hard to get right at scale. That's what makes it such a killer interview question. Before we design anything, let's nail down what this system actually needs to do. Functional requirement number 1, job CRUD. Clean APIs to create, read, update, and delete jobs. Standard stuff. Number 2, scheduling. We need both one-time jobs like send this in 5 minutes and recurring ones with cron expressions like every Monday at 9 a.m. Number 3, timely execution. If a job is supposed to fire at 3 p.m., it fires at 3 p.m., not 3:05. Within a few seconds, that's our target. Number 4, retry with Backoff. Jobs will fail. That's life. We need automatic retries with exponential Backoff. And if it keeps failing, dead letter queue. Someone needs to look at it. Number 5, prioritization. A payment job should never be stuck behind a million analytics jobs. Priority levels are a must. And finally, number 6, status tracking. We need to know exactly where every job is pending, queued, running, completed, or failed. Full lifecycle visibility. Now the non-functional requirements. This is where things get spicy. Scalability. We're talking 100 million jobs per day. Not a typo. Reliability. At least once execution. If a job is scheduled, it runs. No silent fallos. Ever. Low latency. Jobs fire within seconds of their scheduled time, even under heavy load. Fault tolerance. Nodes will crash. Networks will partition. The system keeps running through all of it. And observability. Full metrics, traces, alerts. If something's going wrong, we know before our users do. All right, let's build our high-level design piece by piece. Starting with FR1, job CRUD, the foundation. We need 3 layers. First, an API gateway. This is our front door. Handles off, rate limiting, and routing. Behind that, a job service. This is where the real logic lives. Validation, idempotency checks the actual CRUD operations. And at the bottom, a jobs database. Postgres stores job ID, payload, schedule expression, and current status. REST endpoints, post to create, get to read, put to update, delete to remove. Clean, simple foundation to build everything on. Now, how do jobs actually get scheduled to run? We add a scheduler service. Think of this as the brain of the whole system. Every second, it pulls a time partition index for jobs that are due. Here's the flow, step by step. Step 1, query the database for due jobs. Step 2, atomically mark them as queued with a row lock. No other scheduler can grab the same job. Step 3, push job references into a ready queue. And Step 4, for recurring jobs, calculate the next fire time from the cron expression. Rinse and repeat every single second. Jobs are in the ready queue. Now who runs them? We add a worker pool with task runners. Workers pull from the queue using a competing consumers pattern. Whoever grabs it first runs it. But before executing, each worker acquires a distributed lock. This prevents the same job from running twice. Then it executes the payload. Could be an HTTP callback, a gRPC call, or publishing to a message bus. When done, update the status, completed or failed, with result metadata. Each piece has one clear responsibility. What happens when jobs fail? And they will. That's where the retry evaluator kicks in. Job fails. We check. Have we hit max retries yet? If not, the Backoff calculator computes the delay. Classic exponential Backoff. Base times 2 to the power of the attempt plus jitter. So 1 second, then 2, then 4, 8, 16, 32, giving the downstream service more breathing room each time. But if all retries are exhausted, dead letter queue. It sits there until someone investigates. We also wire in a priority classifier. P0 critical, P1 standard, P2 bulk, and a status state machine tracking the full life cycle. Nothing falls through the cracks. Now the big question, How do we handle 100 million jobs a day? 3 big moves. First, a consistent hash router with jitter injection. Spreads jobs evenly and adds randomness to prevent those spikes. Second, sharded schedulers. Instead of one scheduler, we split across 4 or more shards. Shard A handles 0 to 25 million, B handles 25 to 50, and so on. Each completely independent. Own queue, own workers. If one goes down, the others keep running. Third, auto-scaling worker pools with Kubernetes HPA. Scaling from 3 to 50 workers based on queue depth, plus partitioned database storage. No single component is a bottleneck. Reliability. This is non-negotiable. No job is ever silently lost. For schedulers, leader election through Zookeeper or Ect. Each shard has one active leader and hot standbys. Leader Dis. Automatic failover in under 10 seconds. 4 workers. Heartbeats to Redis every 5 seconds. If a heartbeat stops, a stale job reaper reclaims those jobs immediately. On storage, synchronous replication. Primary with 2 red replicas, plus WEL archiving for point-in-time recovery. Our guarantees. At least once execution, best effort exactly once with idempotency keys, 0 data loss, and auto failover under 10 seconds. Rock solid. How do we keep things fast, especially during those peak spikes? Here's a clever trick. The scheduler prefetches the next 60 seconds of jobs into an in-memory min heap. When a job is due, it's already right there in memory. No database round trip. Workers maintain pre-warmed connection pools. 0 cold start. Now, fault tolerance. Circuit breakers between workers and downstream services. Service starts failing? The circuit opens. We stop hammering it, preventing cascades. Bulkhead pattern. Separate thread pools per target, so one slow service can't star the others. Execution timeouts. Kill anything running longer than 30 seconds. Queue depth alerts. And graceful degradation. Under stress, shed bulk jobs first, protect the P0 queue. SLA targets. P50 under 100 milliseconds, P99 under 2 seconds, 99.99% availability, failover under 10 seconds. Last piece, observability. You can't fix what you can't see. Every service emits telemetry through an OpenTelemetry collector. This feeds into 3 pillars. Prometheus for metrics. How fast? How many? How often? Yelk or Loki for structured logs. What happened and why? And Jaeger or Tempo for distributed tracing. Follow a job across every service hop. Everything visualized in Grafana, with Alert Manager pushing to PagerDuty and Slack when things go sideways. Key metrics, jobs scheduled, execution duration, queue depth per tier, failure rates, scheduler poll latency, and stale jobber claims. If anything's off, we know immediately. Let's put some real numbers to this. A startup might have 100 jobs a day. No big deal. A growing product? 10,000. Still manageable. Hit product market fit? Now you're looking at 1 million. And at hyperscale, 100 million jobs. Every single day. But here's the question that keeps engineers up at night. What happens when all 100 million of those jobs want to fire at the exact same time? And that brings us to the hotcake problem. Look at this chart. See that massive spike at midnight? That's because everyone schedules their cron jobs at midnight. Every hour mark gets a spike. Every 30-minute mark, too. It's a thundering herd. Millions of jobs triggering in the same second. The system goes from idle to completely overwhelmed just like that. So how do we fix it? That's exactly what we're about to design. Let's start with a simple approach. One queue, a few workers, one database. Watch what happens when those jobs flood in. Queue backs up immediately. Workers start running out of memory. Database connections? Exhausted. And boom, system overloaded. Queue backlog, worker OM kills, connection exhaustion. Everything grinds to a halt. The naive approach is a non-starter at scale. Let's build it properly. Let's deep dive into solving the hotcake problem. Solution 1, Sharding. Take that single scheduler and split it into multiple independent ones using consistent hashing. Each shard gets its own queue, workers, and database partition. Why does it work? Horizontal scaling. Need more capacity? Add a shard. Fault isolation. One shard goes down, the rest keep running. And no single bottleneck. The load just spreads evenly. Solution 2, time bucketing and jitter. This one's elegant. Instead of firing 10 million jobs at midnight on the dot, we add a random offset to each one. Actual fire time equals scheduled time plus a random value within a jitter window. Look at the before and after. Before, that massive spike, 10 million jobs at once. After, smooth, even distribution. About 1.4 million per bucket. Totally manageable. And the code? One line. Actual fire time equals scheduled time plus random 0 to jitter window. One line of code that transforms your entire traffic pattern. Solution 3. Multi-level queues. Not all jobs are created equal. So we split into 3 tiers. Priority queue. Payments security alerts. Processed immediately. No rate limit. Standard queue. Regular scheduled jobs. Rate limited to 50,000 per second. Bulk queue. Analytics cleanup. Rate limited to 10,000 per second. Critical jobs are never delayed by bulk work. And the rate limits protect downstream services. Clean and effective. And here's the complete picture. Everything put together. Clients hit a load-balanced API gateway. Hash router with jitter distributes across shards. Each shard runs its own scheduler with multi-level queues and auto-scaling worker pools. Failed jobs flow through Retry with exponential backoff, then to the dead letter queue. Storage is partitioned. Redis handles locks and rate counters, and the monitoring layer watches everything. This handles 100 million jobs a day, stays responsive during peak load, and self-heals from failures. Let's recap the key takeaways. 1. Shard your schedulers. No single scheduler handles everything. 2. Add jitter to fire times. Turn spikes into smooth, predictable load. 3. Multi-level priority queues. Payments never wait behind batch analytics. 4. Rate limit at every layer. Protect downstream from the thundering herd. 5. Auto-scale workers based on queue depth. And always remember, design for the spike, not the average. That's the golden rule. If you found this helpful, smash that like button and share it with someone prepping for system design interviews. Subscribe to System Design Visualized for more deep dives like this. And hit that bell icon so you never miss a new video. Thanks for watching. See you in the next one.